How are you today? Today we are going to discuss on how uh, protic solvents affect nucleophilicity of anions in SN2 reactions. So in contrast to protic solvents, aprotic solvents are those solvents without OH or NH groups, and they enhance the nucleophilicity of anions. So that is different. For the protic solvents, they reduce the nucleophilicity of anions, but for aprotic solvents, they enhance the nucleophilicity of anions, and you'll see why. An anion is more reactive in an aprotic solvent because it is not so strongly solvated. So in this case, of course, when you have aprotic solvent, that is, those are the ones which are non-polar solvents. They don't easily form hydrogen bonds with the anions to drag them from attacking from the backside of the electrophilic atoms. So these ones do not form hydrogen bonds. And because of that, then the anion will easily donate electrons to the electrophilic carbon. So there is no hydrogen bonds to be broken when the solvent must make way for the nucleophile to approach the electrophilic carbon atom. So there is no solvent to remove so that it makes way for the nucleophile to attack the electrophilic carbon. So the relatively weak solvating ability of a protic solvent is also a disadvantage. Most polar ionic reagents are not soluble in simple aprotic solvents like alkanes. So one of the disadvantages of this type of solvents is that you find, again, we have talked about the experiment you did in first year that like dissolves like. So if you have aprotic solvents, most of them which are non-polar like alkanes, any alkane is a non-polar solvent. So if you have to dissolve it in polar reagents like an alkyl halide or the nucleophile, which is also polar, it is not possible. They don't easily dissolve. So that is a major disadvantage. And remember, for the two to react, that is the nucleophile and also the alkyl halide, they have to collide. And if they are not able to mix properly in the solvent, then they will not be able to come into contact for them to react to form a new bond. So that is a major disadvantage. But the only good thing is that for them, there's no formation of hydrogen bonds, so you don't need to strip off the solvent molecules for the nucleophile to attack from the backside. So the solution to this, to protic solvents and aprotic solvents, is polar aprotic solvents. So for polar aprotic solvents, they have strong dipole moments to enhance solubility, yet they have no OH or NH groups to form hydrogen bonds with an ion, as we saw in the case with protic solvents. So the fact that they are able to dissolve, because they have strong dipole moments, they are able to dissolve the polar reagents, that is the alkyl halide and also the nucleophile, because of the dipole moments. But at the same time, they don't have OH or NH groups, so they don't form hydrogen bonds with the anions or with the nucleophiles. Examples of useful polar aprotic solvents include acetonitrile, dimethylformamide, acetone, etc. There are others. So these are the most common polar aprotic solvents. They are polar because you can see in this case, this portion of the molecule, there is carbon which is bonded to nitrogen. So this bond is polarized. So here there's a partial negative and then partial positive. And because of that dipole moment between in this molecule, it's able to easily solvate, not so strongly, but it's able to solvate the alkyl halide and also the nucleophile, which are polar. So all of them, they have that. So this is polar because this carbon is attached to oxygen. So there's partial negative, partial positive. Similarly, partial positive, partial negative. So because of this end of the molecule, they are able to dissolve the alkyl halide or the reagents, that is the alkyl halide and also the nucleophile. So we can add specific solvating reagents to enhance solubility without affecting the reactivity of the nucleophile. So one of the things you have to note is that these polar aprotic solvents are not they can solvate the reagents, but not as well as the protic solvents. But the only problem we saw with protic solvents is that they drag the nucleophile because of formation of hydrogen bonds. Then the non-polar, we say the aprotic solvents, they don't dissolve the reagents at all. Then polar aprotic, they dissolve, but not to a very big extent, but at the same time, they don't form hydrogen bonds to drag the anions. So sometimes to enhance solubility, what happens is that we are the specific solvating reagents can be added to enhance solubility without affecting the reactivity of the nucleophile. So for example, you have what is known as crown ether. This specific one is 18 crown 6, specifically solvates the potassium ions. So this is how it solvates the potassium ions. So because if it was not solvated, what will happen is that potassium halide will form, and then therefore, of course, dragging also the halide ions from attacking the electrophilic carbon from the backside. So instead, when this is trapped, then this becomes free to flow and form new bonds with the electrophilic carbon towards formation of the alkyl, towards the formation of the product. So this is solvated, the potassium ions, and this is known as 18 crown 6 because it has 6 oxygen atoms, and 18 because the total number of atoms in this particular ring is 18. So the following example shows how fluoride ion, normally a poor nucleophile in hydroxylic or protic solvent, can be a good nucleophile in an aprotic solvent. So we've already discussed and seen that when you have the fluoride ion, they are very poor in protic solvents because of the fact that they are dragged by, they form hydrogen bonds with the solvent or protic solvent, and it drags it from attacking the electrophile from the backside. So although potassium fluoride is not very soluble in acetonitrile, 18 crown 6 solvates potassium ions, and the poorly solvated and therefore nucleophilic fluoride flows. So this is the example when you have this alkyl halide reacting with potassium fluoride in 18 crown 6. The presence of this solvent is a polar aprotic solvent, and it's able to solvate to some extent this particular reagents, all these reagents, but not very effectively. But that's why you have this 18 crown 6, which enhances the solubility of the reagents in the solvent. So finally, you get halogen exchange reaction where the fluoride substitutes the chloride to form this particular product. And so one of the things for SN2 reactions, you've seen clearly, the best solvent is not the protic solvent, it's also not a protic solvent, but polar aprotic solvent. Those are the best solvents for SN2 reactions. And of course, I've also said for SN2 reactions, the substrate and also the nucleophiles should not be hindered. So we'll stop there also today, then we'll continue with the rest of the discussions in later lectures.